Good morning all. Today we have the concept of the fundamental theorem of arithmetic, the proof of the theorem, and we have the concept of the canonical decomposition of integers, and we have to do some problems related with canonical decomposition of integers. Let's move to the proof of arithmetic, fundamental theorem of arithmetic. Before going to the theorem, we have some lemmas associated with the theorem. So first lemma is Euclid's lemma. If P is a prime and P divides AB, then P divides A or P divides B. Next lemma is let P be a prime number and P divides A1, A2, etc. An, where A1, A2, etc. A are positive integers. Then P divides AK for some K where 1 less than or equal to K less than or equal to N. And the next lemma is if P, Q1, Q2, etc. Qn are all primes and P divides Q1, Q2, etc. Qn, then P equal to Qk for some K where 1 less than or equal to K less than or equal to N. Now we have the statement of fundamental theorem of arithmetic. It's also known as unique factorization theorem. The statement is every integer, positive integer, n greater than 1 is either is a prime or can be expressed as a product of primes. The factorization into prime is unique except for the order of factors. For the proof, we have the proof consists of two parts. First, the existence part and the uniqueness part. So first we must establish the existence of a factorization into primes for every positive integer n greater than 1, and we must show that it is indeed unique except for the order of factors. Now to show the existence part, let's prove the existence part by the method of strong version of induction. So we are taking the statement let P of n denote the statement that the positive integer n greater than or equal to 2 is a prime or can be expressed as a product of primes. Since 2 is a prime number, clearly P of 2 is true. Now we have as induction hypothesis, let's assume that P of n is true for every positive integer n less than or equal to k, where k greater than 2. Then P of 2, P of 3, etc. P of k are true. That is, every integer 2 through k either is a prime or can be expressed as a product of primes. Now we have to show the theorem is true for P of n is true for the integer k plus 1. For that, consider the integer k plus 1. If k plus 1 is prime, then P of k plus 1 is true. Now assume that k plus 1 is composite. Then k plus 1 equal to AB for some integers a and b where 1 less than a comma b less than k plus 1. So by induction process, a and b either are primes or can be expressed as a product of primes. All these numbers a and b are less than k plus 1. So our induction process hypothesis shows that they are all primes or can be expressed as a product of primes. Hence, in any case, k plus 1 equal to ab or can be expressed as a product of primes. Thus, P of k plus 1 is true. Hence, by strong induction, P of n is true for every integer n greater than or equal to 2. Now, we have to show the uniqueness of the theorem. Now, for that uniqueness part, let n be a composite number with two factorization into primes. That is, n can be written as P1, P2, etc. Pr, which is equal to Q1, Q2, etc. Qr, where all P1, P2, etc. Pr are primes. Similarly, Q1, Q2, etc. Qs are primes. We will show that R equal to S and every Pa equals some Qj where 1 less than or equal to I comma j less than or equal to R. That is, the primes Q1, Q2, etc. Qs are a permutation of the primes P1, P2, etc. Pr. Assume for convenience that r less than or equal to s. Since p1, p2, etc. pr is equal to q1, q2, etc. qs, p1 divides q1, q2, etc. qs, and hence by the lemma stated in the third lemma, we have already stated in the first slide, if p, q1, q2, etc. qn are all primes and p divides q1, q2, etc. qn, then p equal to qk for some k, where 1 less than or equal to k less than or equal to n. Using that, we got p1 equal to qi for some 1 less than or equal to I less than or equal to s, dividing both sides p1 by qi. So we get here left side we are dividing with p1, so p2, p3, etc. pr. Right side we are dividing with qi, so q1, q2, etc. up to qi minus 1, that qi is not there, qi plus 1, etc. qs. Now p2 divides RHS, so again by lemma p2 equal to qj for some j, dividing both sides p2 by qj, we get p3, p4, etc. pr is equal to q1, q2, etc. qi minus 1, qi plus 1, etc. qj minus 1, qj plus 1, etc. qs. Since r less than or equal to s, continuing like this, we can cancel every pi with some qj. This yields, so every pi's we are dividing, so finally we will get 1 at the left hand side. This yields 1 on the left hand side at the end. Then RHS cannot be left with any prime, since a product of primes can never yield a value 1. So left side is 1, so the right side should be equal to 1, otherwise it will be 2. If 2 numbers are there, then the product will be, then 2 primes are there, then their product will not be, we will not get the product as 1. So the right hand side should be equal to 1. So we must have exhausted all qk's by now. Therefore r equal to s, and hence the prime q1, q2, etc. qs are the same as the primes p1, p2, etc. pr in some order. Thus factorization of n is unique except for the order in which the primes are written. Now we have the definition of canonical decomposition. The canonical decomposition of a prime integer n is of the form n equal to p1 raised to a1, p2 raised to a2, etc. pk raised to ak, where p1, p2, etc. pk are distinct primes with p1 less than p2 less than etc. pk, and each component ai is a positive integer. First problem is find the canonical decomposition of 15,435. We can write 15,435. We have to divide it by the least prime number. So it is not divisible by 2. The sum of these these numbers, 1 plus 5, 6, 6 plus 4, 10, 10 plus 3, 13, 13 plus 5, 18, which is a which can be divisible by 3. So this when we divide by 3, the answer is 5, 1, 4, 5. Now when we add this number, 5 plus 1, 6, 6 plus 4, 10, 10 plus 5, 15. Again it can divide by 3, so it's 3, 1, 7, 1, 5. Now when we add these numbers, 1 plus 7, 8, 8 plus 1, 10, 10 plus 5, 15. So it's not a multiple of 3, so we cannot divide by 3. So next prime, possible prime is 5. In the unit place the value is 5, so it can be the number 1750 is a multiple of 5, so we can divide it by 5. So this is 3, 21, 4, 15, 3. Now it cannot be divisible by 3. Now next possibility is 7, 49, 7, 7. So this is 154. The number is 15435. So 15435, we could write it as 3 square into 5 into 7 cube. So this is the canonical decomposition of decomposition of 15,435. Next problem is find the canonical decomposition of 2,520. We can use the same method, or we could write 2,520 is equal to, this is 40 into 63. So we know it is division by 10. Now it's divisible by 4. So 252 by 40 is 25. 6 in 12, it is 3. So this can be written as 8 into 5 into 7 into 9. So this is 8 is 2 cube into 5 into 7 into 3 square. Now we could write this canonical. The all small prime should come first. So 2 cube into 3 square into 5 into 7 is the canonical decomposition. So we can do in the earlier problem 2000. If it is in this way, 2,520, we could divide by 2. So this is 1, 2, 6, 0. Again divide by 2. So this is 6, 3, 0. Again divide by 2. 3, 1, 5. Again divide by 3. So the answer is 1, 0, 5. Again we can divide by 3. So the answer is 3, 5. Again we can divide by 5, 7. So 2 raised to 3 into 3 raised to 2 into 5 into 7. 2,520. This is the same answer we got earlier. Next problem is find all positive factors of 315. First find the canonical decomposition of 315. For that we can divide by, first we can divide by 3, then it is 105. Again we can divide by 3, then it is 3. So this is 35. Now we can divide by 5 and 7. So 315 is equal to 3 square into 5 raised to 1 into 7 raised to 1 is the canonical decomposition, or we can canonical decomposition. By the fundamental theorem of arithmetic, every factor of 315 is of the form 3 raised to A, 5 raised to B, 7 raised to C, where 0 less than or equal to A less than or equal to 2, 0 less than or equal to B less than or equal to 1, and 0 less than or equal to C less than or equal to 1. Therefore, factors of 315 are 3 raised to 0, 5 raised to 0, 7 raised to 0. which is equal to 1. Next 3 raised to 0, 5 raised to 1, 7 raised to 0, which is equal to 5. Now 3 raised to 0, 5 raised to 1, 7 raised to 1, which is equal to 35. Now 3 raised to 0, 5 raised to 0, 7 raised to 1, which is equal to 7. Now 3 raised to 1, 5 raised to 0, 7 raised to 0, which is equal to 3. 3 raised to 1, we can fix 3 raised to 1. So 5 raised to 1, 7 raised to 0, which is equal to 3 into 5, 15. Next 3 raised to 1, 5 raised to 1, 7 raised to 1, 3 into 35, which is equal to 105, 15 into 7, 35 into 3, 105. Now next 3 raised to, we can fix 3 raised to 2. Then 3 raised to 2 into 5 raised to 0, 7 raised to 0, which is equal to 9. 3 raised to 2, 5 raised to 1, 7 raised to 0, which is equal to 45. 3 square into 5 raised to 0 into 7 raised to 1, which is equal to 63. Next same 3 square into 5 raised to 1 into 7 raised to 1, which is equal to 315. Now one thing is missing is 3 raised to 1, 5 raised to 0, 7 raised to 1, which is equal to 21.